Sine of theta plus squared plus cosine theta squared is 1. 1 plus tangent squared theta is secant of theta squared, or secant squared theta, however you want to say it. 1 plus cotangent theta squared is cosecant of theta squared. The sine of alpha plus beta, sine of alpha cosine beta plus cosine alpha times sine beta. Or sine of the first, cosine of the second, plus cosine of the first, sine of the second. If you say that over and over again, you don't have to change what you're saying based on the Greek letters of the angles or the specific angle measurements. And hearing the same thing over and over again in your head might help that memory go on. If this is subtraction, your right-hand side of the identity will be subtraction. The cosine of alpha plus beta, cosine alpha, cosine beta, minus sine alpha, sine beta. Not quite the choral answers I was expecting, but then again, getting 30 people all to say the exact same thing at the exact same moment might not sound too pretty. If you have a cosine of a difference of angles, the right-hand side of your identity will be addition. The tangent of alpha plus beta. Tangent of, okay, somebody needs to talk to me. Alpha plus tangent of beta over 1 minus tangent alpha, tangent beta. Sine of 2 theta. 2 sine theta, cosine theta. Cosine of 2 theta. Cosine of theta squared. Minus sine theta squared. You guys are saying these better than I did. Cosine of 2 theta in terms of cosine. 2 cosine theta squared minus 1. And cosine of 2 theta in terms of sine. 1 minus 2 sine of theta squared. You want to just simply sort of quote-unquote derive the tangent of 2 theta based on the sum and difference identity for tangent, specifically the sum one. Tangent of 2 theta. 2 tangent theta over 1 minus tangent of theta squared. The sine of theta over 2 is a plus or minus. It is a square root. What's inside? 1 minus cosine of theta over 2. You derive this rule from the cosine of 2 theta in terms of sine. Cosine of theta over 2, plus or minus square root of 1 plus cosine of theta over 2. The tangent of theta over 2, knowing that tangent is sine over cosine, is plus or minus what? Square root. Sine over cosine, the divisions of 2 cancel out. 1 minus cosine theta over 1 plus cosine theta. And there's 2 more identities that we derive out of that. How about the one with the sign in the denominator? 1 minus cosine theta. 1 minus cosine theta over sine of theta. This is the identity that you always want to use. You don't have to, but strongly suggested. This is the identity for the tangent of theta over 2 that you want to use if you're doing a problem that's, evaluating angles off of a unit circle. How about the one with the binomial in the denominator, or the 2 terms in the denominator? What's the other version? Sine of theta over, come on, why are you guys getting so quiet? 1 plus cosine theta. What is the sine of theta squared, these power reducing formulas? 1 minus cosine of 2 theta over 2. And then cosine of theta squared is cosine of 2 theta plus 1 over 2. And the tangent of theta squared is equal to 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. Okay, so we derived all those yesterday. Now we just have to know them and use them. Again, those of you that take the route of doing AP Calc AB or BC next year, you are going to be needing to have those memorized. We have the equation. We want to solve for x on the interval from 0 to 2 pi. And we have the sine of 2x is equal to the square root of 3 over 2. Now, when you have a singular trig function solved for and set equal to, some kind of value, this one's off the unit circle, it might be a question that you're doing with your calculator. The multiple on the angle is the number of times you go around the unit circle. So we're looking for values of x that are between 0 and 2 pi. Of course, to get the 2x out of the sine function, you apply an arc sine. So 2x is equal to arc sine or inverse sine of square root of 3 over 2. We've done a lot of unit circle work, so I know this is not going to be a problem. Parts of a triangle go into an inverse trig function and out comes an angle. So what angles around the unit circle give sine values of square root of 3 over 2? Is that? So these are the angles from inverse sine, once around the unit circle, but we're looking for x between 0 and 2 pi. Our last step is to divide by 2. So when we divide by 2, we're going to get pi over 6 and 2 pi over 6. Or if we go that second trip, pi over 3, 2 pi over 3, 3 pi over 3, 4, 5, 6, 7 pi over 3. And then what? 8 pi over 3. Or take these two original answers and just add 2 pi. I like to just keep counting around the unit circle. Now you divide everything by 2, and x is equal to pi over 3 divided by 2 is pi over 6. 2 pi over 3 divided by 2 is 2 pi over 6. 2 pi over 6. Oh, my math was wrong a second ago. And then 7 pi over 3 divided by 2 is 7 pi over 6. And 8 pi over 3 divided by 2 is 8 pi over 6. Or in reduced form, we have x is equal to pi over 6 pi over 3, 7 pi over 6, and what? 4 pi over 3. So when you're solving multi-angle identity equations with multiple angles in them, we're going to see more advanced problems in a second, but if it's just that one trig function, the multiple on the angle is simply how many times you go around the unit circle. So I hope that makes sense, but just to make sure, let's do one more. For our second example, we have the tangent of x over 2 is square root of 3 over 3. And we're going to get that angle of x over 2 out of the tangent function by applying a inverse arctangent. So inverse tangent, just to keep you comfortable with that notation, of square root of 3 over 3. So x over 2 is equal to what? How many times are we going around the unit circle? Okay, you answered a question I wasn't asking, but I'm going to ask that next. X over 2 is a multiple of 1/2 x. And I know you know the answer to this too because I just said it. How many times are we going to go around the unit circle? A half a rotation. So we have a ratio which is positive. We have a ratio of square root of 3 over 3. So the inverse tangent of square root of 3 over 3 is, you just said it, pi over 6. So we got 1/2 x is equal to pi over 6. Why are we not going to go over to quadrant 3 and include that 7 pi over 6? Well, this is why. If you do go all the way around the unit circle one time, ignoring that 1/2 multiple on the x, you're going to be okay. You'll have actually the answers you need plus a couple, maybe 1 or 2 extras that you just have to recognize you need to eliminate. So as we continue solving for x and multiplying both sides by 2, we get x is equal to pi over 3, and what? 2 times 7 is 14 pi over 6. Well, we're looking for solutions of x that are between 0 and 2 pi that I just erased because I wrote the wrong problem. And 14 divided by 6 is what? Compared to 2? Bigger. So this answer you can consider maybe as extraneous. It's outside the domain that we were given in the directions. So the only answer is pi over 3. We've got another question where we're solving for x on the interval from 0 to 2 pi. And it is the sine of 2x is equal to the cosine of x. You've got 2 trig functions, and even if you had the same trig function, you have 2 different size angles. You are never going to solve this equation, first of all, if you've got trig functions with different size angles, just like your identities. If you start seeing sum and difference with single angles or single angles with half or double angle identities, step number 1, job number 1, get these angle measures to be the same. So how can we write the sine of 2x, this is a double angle trig function, into a trig function in terms of single angles? Sine of 2x.
You can replace it with
Substitute with.
Yeah, substitute with 2 sine x cosine of x.
Cool. All right. How do we solve nearly, you may not seem like it when you're in Algebra 1, but how do you solve the vast majority of equations in math? You have to set them equal to, if we have multiple equations, we'd set them equal to each other. But no, we want to set them equal to 0. So we're moving this cosine over with subtraction, and we have 2 sine of x cosine of x minus cosine of x is equal to 0. And if we're lucky, after we take our equation and set it equal to 0, we can do the F word. Factor. So what can we factor out of these 2 terms?
Cosine of x.
The cosine of x. Now, we have one equation with 2 variables defined by 2 different trig functions. That might cause a problem or cause a lot of extra work, but in this case, we can factor out that cosine of x and get 2 factors, each with their own individual trig function, meaning we can set these equal to 0 and solve each one of them. Now, I'm going to admit, it's not good form or good habit, but all of your answers, you do need to put them back into your original equation and make sure that they all work and that you don't have any extraneous solutions. I didn't do that check before picking all these examples, so I hope I don't get myself in trouble. Where is x? If x is arc cosine of 0, where on the interval between 0 and 2 pi is cosine giving us an answer of 0? Pi over 2 and 3 pi over 2. Where on the unit circle, I'm going to not write the inverse sine line here. Where on the unit circle is sine equal to 1/2? pi over 6 and 5 pi over 6. You guys are on fire. I love it. Okay. Our next example, we've got, and I think I did something similar to this the other day, but I've got so many classes doing similar work, I've lost track. We've got the cosine of 2x plus 5 cosine of x plus 3 is equal to 0. How do we get this equation set equal to one trig function? Now, we have one trig function, excuse me. Both of these terms have a cosine, so you might be like, great, I can factor this or do whatever, but double angle, single angle. This might as well be like cosecant. I mean, it's totally, kind of, sort of, totally different. Until you get these angle measures to match, and they can be 2x and 2x. If it was cosine of 2x plus 5 cosine of 2x, I just add those like terms, subtract 3, do some work, and just, ultimately do like an inverse cosine. But single and double angle together, we need to fix that. So, let's take the cosine of 2 theta out. We have three versions for the cosine of 2 theta. Let's use the one that keeps this equation in terms of one trig function. I do not want to introduce the function of sine into my next line of work because I'm going to not be in a place where I can't continue the problem, but I will be adding more steps to my work. So nice job. We're going to take cosine of 2x out and substitute in its place 2 cosine of x squared minus 1 plus 5 cosine of x plus 3 is equal to 0. Adding like terms, we have 2 cosine of x squared plus 5 cosine of x plus 2 is equal to 0. And I've done a lot of very meticulous review of factoring. Today I'm trying to do a lot of different style of problems. So factors of 2 cosine of x squared is 2 cosine of x and 1 cosine of x. This other constant factor of 2 is also prime, and I want to put the factor of 2 in a place that's going to multiply with this factor of 2. So that's coming over here to the second factor. We have a 1 here. Everything is positive. Everything is plus. And now that's that quadratic factored. We're going to set each factor equal to 0. We get cosine of x is negative 1/2. Cosine of x is negative 2. What do you put into a trig function? An angle measure. What do you get out? Parts of a triangle. What two parts do you get out of cosine? An adjacent leg over the hypotenuse. A small leg over a big hypotenuse is never going to give you an answer that's what? Greater than 1 or less than negative 1. This is outside the range of your cosine function, so this small equation has no solution. And we have here x is arc cosine of negative 1/2. And I mean, we're at the end of chapter 5. The test is right around the corner. And you guys are like, I mean, you're not even hesitating with these answers that you're verbalizing. That's awesome. Inverse trig function, parts of the reference triangle in, angle out. What angle around the unit circle between 0 and 2 pi gives cosine values of negative 1/2? 2 pi over 3 and 4 pi over 3. Nice. All right. Let's go on to some proofs. Whoop, whoop. Love me some proofs. Actually, let's not do a proof. Let's evaluate and more unit circle work. if I ask you for the sine of 15 degrees, you have an option of how to do that problem. Because what two angles subtract to give you 15 degrees? Whoops. That could be the sine of 45 degrees minus 30. And somebody else might do the sine of 30 degrees divided by, what's that supposed to be? 30 degrees divided by 2. So sometimes when we are given a trig function with an angle inside, we have multiple ways of doing the same problem. But I want to give us an example where we don't have that option. If you have the option, by all means, use whatever identity you prefer. I know you thought that was going to be the next example. For our next example, we have the cosine of 157.5 degrees. Whoop, whoop. Okay. This is a decimal, and you're not going to, think about the degree angles around the unit circle. They're all integers, so you're not going to add and subtract two integers and get a half unit. So now this is one thing I always think is a little bit weird about the use of the half angle identities. If you double 157.5, you get 315 degrees. I honestly, once you do these for a day or two, you won't hesitate with that. But I did glance down and make sure I knew the answer. 150 is 300, and 7.5 and 7.5 is 15. So this problem can only be solved, without a calculator. If I give you this and I say, give me an answer in exact format, anything that do something in trig and yield an answer in exact format means you have to be using the unit circle. And you're going to utilize a half angle identity to do this problem. But to utilize the half angle identity, you need to double the given angle, which is kind of weird. You have to double this to use the half angle identity. So the cosine of 157.5 is the cosine of 315 degrees over 2. The 315 degrees is the theta that we're going to use in the other side of this identity. So the cosine of 315 over 2 is equal to, now it's plus or minus, we'll clarify that in a second, plus or minus the square root of 1 plus the cosine of 315 degrees over 2. Now, our work on the right-hand side is going to involve a 315 degree angle. But how we choose whether this answer is going to be positive or negative, first of all, lost track. In what quadrant is 315 degrees? 4. Quadrant 4. And in quadrant 4, cosine will be positive because it's x over r. But we're looking for an angle, the value of cosine and angle, the value of cosine in quadrant 2. And in quadrant 2, cosine is negative. So our answer will be negative. Don't pay attention to the fact that you're using 315 degrees to finish this problem. Not for the positive, negative nature of your answer. So if you know the unit circle, the rest of this hopefully is very easy. 1 plus, what's the cosine of 315 degrees? Square root of 2 over 2. And that's all over 2. Well, once you start seeing fractions show up, you should make everything look like a fraction. So I'm going to do two things. I'm going to write the denominator as a fraction, but I'm also going to find a common denominator in the numerator and add these two fractions. because I don't know, it's the way I like to do it. There's slight variations in how you simplify this. This is what I like to do. 2 over 2 plus square root of 2 over 2 is 2 plus square root of 2 over 2. That's being divided by 2 over 1. We're going to take that denominator, and instead of dividing by 2 over 1, we're going to multiply by 1/2. And we have negative square root of 2 plus square root of 2 over 4, right? Because 2 times 2 is 4. But what's the square root of 4? 2. So our final answer is the cosine of 157.5 is negative square root of 2 plus the square root of 2 over 2. That's our final answer. So you're going to have to keep practicing your skills with fractions. The tangent of 7 pi over 8. Is there anything on the unit circle, any radian measure on the unit circle that has a denominator of 8? No. But if you do 7 pi over 8 and multiply it by 2 over 1, what do you get? 7 pi over 4. I'm not going to do 7 times 2 is 14. I'm going to do 2 over 8 reduces to 1/4. So that's going to be the tangent of 7 pi over 4 over 2. And the 7 pi over 4 is your theta. Okay, I'm trying to get at least one proof in before the bell rings. We're not doing a proof. I absolutely do not want to work with radicals inside of a big radical. And if I need to rationalize the denominator, I don't really want to do that by having to multiply by a conjugate, which you probably will if you use sine of theta over 1 plus cosine theta. So when you're doing a problem where you're evaluating tangent off the unit circle, you're not doing a proof, you're not solving an equation, you're just doing an evaluation of an angle, this form of by far the easiest one to use. So the tangent of 7 pi over 4 divided by 2 is going to be calculated most easily by 1 minus the cosine of 7 pi over 4 divided by the sine of 7 pi over 4. Now, what's the cosine of 7 pi over 4? Square root of 2 over 2. You're in quadrant 4. What's the sine of 7 pi over 4? Square root of 2 over 2. Now, I'm not going to finish this problem because I want to do at least one proof with you today. But let's multiply the numerator and denominator by 2 to at least not have fractions within fractions. 2 times 1 is 2. When you distribute to the second term in the numerator, the 2 divided by 2 are going to cancel. So you have 2 minus the square root of 2. And in the denominator, the 2 divided by 2 will cancel, and you'll have the square root of 2. And if you want to rationalize that, it's only one line of work, but I want to do at least one proof before we get out of here. Oh my God! It's illegal, or cops are going to come in and arrest me. Yes. Basically, outside of a textbook, no one really cares. On a standardized test and multiple choice, in solution guide, they always rationalize the denominator. You get to a certain level of math, and your teacher's going to be like, whatever, I don't care. So let's do a proof. We're going to verify or prove.
Just to let you infer the sine of 4, is that negative?
Ah! So the sine of 7 pi over 4 is negative. So it's negative there. Thank you for saving my butt. All right. I did say we were in quadrant 4, and then I wrote a positive answer, so bad on me. Okay. For our next example, we're going to verify that the sine of 2 theta is equal to the tangent, 2 tangent of theta over 1 plus tangent squared theta. You know what I'm going to do? I'm going to do more proofs in 7th period. So I have enough to put a nice long video together that probably nobody will ever watch because it'll be like 45 minutes long. But at any rate, what side do we want to start this proof on, the left or the right?
Right.
Yeah, the right. A lot of times I do say when you have a multiple or a sum of angles, I'd like to start on that side, but I know the sine of 2 theta is 2 sine cosine, and like, how am I going to build that out to like some kind of fraction with trig functions all over the place? So I like everyone's idea. I like this idea. We're going to start this proof on the right-hand side because we have lots of stuff going on. We have 2 tangent of theta over 1 plus tangent of theta squared. And you jumped on that right away. What would you like to do on this right-hand side to get it closer to the left-hand side? If you can involve your Pythagorean identities nearly every time in these textbook-style proofs, you're going to make your life much easier. We have an addition in the denominator. Here over on the left-hand side, we don't even have a denominator. So 1 plus tangent squared is going to come out, and in its place, we're going to substitute secant squared. So 2 tangent of theta over secant squared theta. Somebody else?
Can you rewrite it in terms of sine and cosine?
Yeah, at this point, just sitting the way it is kind of like nothing left to do. So when you get to that point, it's probably a good idea to write everything in terms of sine and cosine. So 2 sine of theta over cosine theta divided by 1 over, let's not forget secant is 1 over cosine. So we have 1 over cosine of theta squared. Instead of dividing by that fraction, we're going to multiply by the reciprocal. We got cosine of theta squared divided by cosine. That's going to offer an opportunity to do some simplification. And oh my gosh, look at there. We are done. 2 sine theta cosine theta. Bam! I love this stuff. No, we're not done. This isn't totally done yet. This isn't an exact match. What's 2 sine theta cosine theta? Sine of 2 theta. You got to go all the way to the end. Sine of 2 theta. Now we're done. Let's do this example. We have the sine of 3y over the sine of y is equal to 1 minus 2 sine of y squared plus 2 cosine of y squared. We're going to verify this. We're going to do this proof. You want to start with the left or the right? There's a lot going on with the right-hand side. But on the left-hand side, we have not triple angles. We have identities for double angles and half-angle identities. So the only way that we're going to be able to bring down this 3y is with the use of one of these sum or difference identities. And as soon as you apply one of these sum or difference identities, you're going to have a lot to work with immediately. So the left side looks less complicated, but it actually is going to open the door to a lot of potential work right off the bat. So even though the right side looks more complicated, and I said with proofs they're puzzles, the solutions that I have worked out actually, it does start with the right. But I can see my work from previous years, and it's not that easy to get through. So let's start this proof on the left-hand side, where we have the sine of 3y over the sine of y. Now, look at where we are and where we're going. What is numero uno that should be a big red flag screaming at us? Okay, well, that is something we're going to have to approach. What are you going to say? There's three terms. Okay. What do these two terms over here both have in common? They have the same.
They're like both of y and then this one.
These both have a measurement of an angle size of just y. Your denominator down here has an angle size of y. This is a triple angle. That's like totally different. Okay? I mean, look at all the work it takes to do the sine of 2 theta is 2 sine theta cosine theta. The cosine of 2 theta is cosine of theta squared minus sine of theta squared. There's a lot of math that has to be done to just change the size of an angle measure. That's why we have, so many of these identities up here. So let's try working not first on the powers that we have, but first trying to get the angles to be the right size. Let's break the 3 down into 1y plus 2y. And why is that cool? Because we have identities for double angles. And when we say that sine of 3y is the sine of y plus 2y, we can work out a sum identity for sine, and then we'll have double angles floating around, and we have double angle identities to work with that. So the sine of two angles added together is what? Sine of the first, cosine of the second, plus cosine of the first, times sine of the second. Now, here's where you got to start thinking about the fact that the cosine of 2 theta has 3 different versions of its identity. We're not really working with half-angle identities right now, but tangent of theta over 2 has 3 different versions to this identity. To look at the sine of 2y and see that this angle is still the wrong size, so what's the sine of 2y? 2 sine y cosine y. There's no choice of what we can do with the sine of 2y. There's only one identity. So we have cosine of y times 2 sine of y cosine of y. So in the second term now, all of my angles are at least the same size, which is probably going into a good direction. And on the first term, we have the sine of y, but we need to get rid of the cosine of 2y. Now, we have, and I honestly don't know what the best choice is, and we might have to come back and change this, but the cosine of 2 theta has 3 different choices. Which of these 3 is potentially going to be the right choice?
The bottom one.
Why?
The answer is already in the answer we're going to.
Okay. The answer, we have a sine squared in our final answer. Are you positive of that answer? Are you positive of that answer?
I hope.
I hope so too.
Not anymore.
If you have any doubt, it might be actually a good idea to not do this substitution like I'm kind of enticing you to do. It might not be a good idea to do this substitution yet because there are 3 choices, and maybe as we go through this process, what we need might be more obvious. So you know what? I'm going to scratch that. Let's take this out and put back in the cosine of 2y. Since we do have choices, I don't want to pull in the choice that makes this longer than it needs to be. What's not up here that's in this current expression? There's a big division. And that means the sine of y needs to go away. Can we cancel out the sine of y right now? Do we have a sine of y in the first term? Do we have a sine of y in the second term? Okay, let's factor that out. And let's pull out the sine of y and have cosine of 2y plus 2. Cosine y is cosine of y squared. And there's a 2 there. So that's good. Over the sine of y. And in our numerator and denominator now, we have a factor of sine of y, and that's going to cancel out. Okay, so now it's painfully obvious that Lucas was right, which makes me very happy. The sign of the division of sine of y is gone. We have that 2 cosine of y squared. Our answer has a 2 cosine of y squared. And what's left up here? 1 minus 2 sine of y squared, and that is actually what we have here. So that substitution was 100% the right one to do. But now we're so close to the final answer, it's not we think the third choice is the best choice. It is, we know. So we get one last substitution. Cosine of 2y comes out, and 1 minus 2 sine of y squared goes in, and we are done with that problem.
That was pretty good.
Bam! That was excellent. Okay. Did anyone do any of the homework from 5.5 and get stuck on something you want me to go over? For our last example, we have the cotangent of u is equal to 3. What do you put into a trig function? An angle. What do you get out? 2 parts of a reference triangle. So even though that's just 3, I'm going to write that as 3 over 1. And we are told that angle u is between pi and 3 pi over 2. And we need to find, let's say, the cosine of u over 2. Okay, so if I can, I'm going to do what? And you should do what? Draw a picture. So, okay, we're going to draw a picture in quadrant between pi and 3 pi over 2. Or quadrant 3. And we're going to draw that reference triangle. Cotangent is adjacent. Oh, this is theta. Or actually not theta, this is angle u. And the cotangent of u, cotangent is adjacent over opposite. So there's a 3, there's a 1. They're both movements left and down in terms of like, there's no such thing as a negative length, but this is a point on the terminal side of -3, -1. So the hypotenuse is going to be the square root of -1 squared plus -3 squared, which is going to be the square root of 10. And the cosine of u over 2 is going to be plus or minus. We're going to clarify that in a second. The square root of 1 plus the cosine of u, which is adjacent over hypotenuse, so plus or minus 3 over the square root of 10 divided by 2. Now, u is in quadrant 3. But we're analyzing the cosine of u over 2. So if u is in quadrant 3, then u over 2 is greater than pi over 2 and less than 3 pi over 4. 3 pi over 4 is here, and pi over 2 is here. So this, somewhere in this region, somewhere in quadrant 2, is where the cosine of u over 2 is. So cosine of u over 2 is in quadrant 2. And in quadrant 2, cosine is what? Positive or negative? Negative. That's how you determine whether you take your answer and keep it as a positive or negative. Okay, so I'm probably not going to simplify this to what's in, and I don't care. So this is going to be negative. I'm going to find a common denominator. I have a square root of 10 up here, so I'm going to do square root of 10 minus 3 over the square root of 10. That's all over 2, or all over 2 minus 2 over 1. So I'm going to multiply, instead of dividing by 2, I'm going to show a multiple of 1/2. And so we have negative square root of the square root of 10 minus 3 over 2 square root of 10. And that is really ugly, but you know what? I'm actually okay with that. I mean, the only thing we might do that I'm going to ask you to do is maybe you can multiply the inside the radical, multiply the numerator and denominator by square root of 10, and get negative square root of 10 times square root of 10 is 10, minus 3 square root of 10 over square root of 10 times square root of 10 is 10, times 2 is 20. Okay, now I'm kind of pausing because there's a perfect square in 20, right? It's 4 times 5. But I'm still going to have some kind of radical within a radical. So 20 is 4 times 5, so you could write negative, the square root of 4 is 2.
You just lost me.
And have square root of 10 minus 3 square root of 10 over 5. But I'm not going to worry about doing any kind of more reduction than just that. What about the tangent of u over 2? We're not doing a proof, so why don't we just use the simplest formula possible? The tangent of u over 2 is going to be 1 minus the cosine of u over the sine of u. So we have 1 minus, what's the cosine of u? Negative 3 over the square root of 10 over the sine of u, which is negative 1 over the square root of 10. So I would multiply the numerator and denominator by just the square root of 10 to cancel these divisions of square root of 10s out. Maybe a negative to go along with it. So negative square root of 10 times 1 is negative square root of 10. Negative and negative make positive. So this is positive, and you have square root of 10 divided by square root of 10, which is 1. But you have a positive term in here getting multiplied by negative 1. So minus 3 over 1. So that's going to be your answer right there.